Welcome back to my channel once again. Today I want us to look at the continuation of 2025 WAEC GCE questions. Of course, this is the part 3. If you have not watched part 1 and part 2, please do me this favor. There is a link in the description below. Please take that link for part 1 and part 2. Then for part 3, we are going to look at question number 9. Remember, each of those parts, they have the different questions solved there. Of course, this is 2025. This is just revision of the questions that was asked in 2025 WAEC May, June for the internal students. It's only for external. Some of these questions, they will repeat some of these questions. That is why we are taking our time to review them one by one. Now, this question number 9, the number 9 says, of course, it is a session B, where we have the long questions there. The question 9A says, state one difference between deformation and elasticity. One difference between deformation and elasticity. Anytime you face this type of question, differentiate. All you need to do is you can use a table to differentiate it. You can write here deformation on this side, while elasticity on this side. And of course, we know that, yes, in the first place, you can say that deformation, this results as a result, you can say it results as a result of, or you can say this occurs. Okay, let's only use the word this occurs. This occurs as a result of applied force. It results as a result of applied force. Whereas the elasticity on its own, we can say that yes, that elasticity is the property of the material. Yes, this is a property of an elastic material. You can take it this way. Either you take it this way, remember, for you to attract, for whatever you have to attract mark, they must merge. That's what we call pair, because they must be correctly paired. Now, the second one, you can say that yes, that deformation, of course, we know that in deformation there is a loss of shape or loss of size. Deformation, this results to loss of the shape and the size. There is a loss of shape or size of the original material. Now, in elasticity, we can say that it is the ability, you can say that it is the ability of the material, to regain, its shape and size. The ability of the material to regain its shape and size after applied force is removed. For elasticity, when you remove the applied force, it returns back to its original shape and size. Whereas for deformation, there is a loss of shape and size after applied force is removed. When you remove the applied force there, it loses its shape and size. Whereas for elastic material, they return back to its elastic, to their former shape and size. The moment you remove the applied force there. For example, if you have, let's say, a sheet of paper, fold the sheet of paper, that is applied force. By the time you remove that applied force there, it will lose its shape and size. There is no two ways about that. But if it were to be a rubber band, the moment you extend it, automatically it will, and then remove that restoring force, it will come back to its original shape and size. Now let us take a look at question number 9b. All right, so we have the 9b. The 9b said the following results were obtained from an experiment performed on a spiral spring. Now, this is the result obtained from a spiral spring experiment. This is the stretching force. This one is the extension. Now, the force is in Newton, extension is in centimeter. Now, we have 0.00, 0.0, 1.0, 2.0, 3.0, 4.0, 5.0, and then 6.0 Newton. The corresponding extensions are 0.0, 5.0, 10, 15, 20, 25, 30. Now, the first question says, that is question I, plot a graph of stretching force on the vertical axis and extension on the horizontal axis. Plot a graph of stretching force on the vertical axis against extension on the horizontal axis. Now, after that, the second question says, determine the slope of the graph. Third question, what does the slope of the graph represent? Now, let us take those questions one after the other. Remember that since it is a WAEC, you will be given a graph sheet where you will do the plotting. So I'm going to do the plotting on the board here, but in case of exam, please use your graph sheet and then your scale, very important, and then how you plot. Now let's take it one after the other. Now the first thing we do is to draw an axis, draw the horizontal. This is a horizontal axis. Now remember, as usual, the moment you do this, get your axis here 0, 0. This has mark. That means you are starting from the origin. Now we have here. Remember, you asked to plot a graph of f on the vertical axis. That means that thing you are asked to plot, please put it there. On no condition should you leave it. And then as you are putting it, put the SI in it as well. Now here we are asked to plot extension. Remember, the extension given to us here is in cm. So if you are going to plot in meters, please always indicate it. Now we pick our axis here. How do we pick our axis? We take a look at the highest value we have here. The highest value we have on f-axis is 6. And of course, we can have here 1, 2, 3, 4, 5, 6. As the case may be. You can say let 2 cm represent 1 unit. So in that case, I can have 1 here, 2 here, 3, 4, 5, 6. Let's say somewhere here, 7. Label your axis to the last value there. Now this one has 30 as its highest value. How do we take it? We can take it 5, 10, 15, 20. And of course, this one is 5, 10, 15, 20, 25, 30. That is how it is. We just bring it there. We can have the 5, 10, 15, 20, 25, 30, 35. Continue it. So we have 5 here, 10, 15, 20, 25, 30, 35. Continue to label it. Now we are done with this. So what we do now, of course, this one is 0, 0. There's no need to plotting it. We move straight to f. When f is 1, what is the extension there? When f is 1, the extension, of course, you can have it like this. You can plot here. Please avoid using dotted lines to trace. Avoid it. The next one is 2 against 10. If we have 2 here, I can have, maybe we have 10 here. You can plot it. Even if you use your dotted lines to trace it, clean it at the end of the day. Next one is 3 against 10. So 3 against 15. So we can plot here. If we do that, clean off this. The next one is 4 against 20. You can plot here. Then clean off the former one. 5 against 25. You can plot here. Then clean off the other ones. Clean them off so that your work will be neat. Now, last one is 30 against 6. So, otherwise, I can put this like this. The under 30, I can have it this another way so that your work will be neat. Now, at the end of the day, you draw your line of best fit. Remember, all of them must not enter the same line. If you look at this, all of them did not enter. So you can draw your line of best fit. Now, that is the line of best fit. Then, remember, they requested for slope. For your slope, just start from anywhere on this line. Start from anywhere there. So, of course, please avoid using just small slope. I can use this one here. Maybe somewhere here. I can have something like this. This is a nice slope. Now, you read what you have here. Read it. At this point, you can use dotted lines. You can use dotted lines at this point. You can use dotted lines here. Now, this one, you can also use dotted lines. So, assuming when I use, of course, dotted line, like I said, is acceptable here. Is acceptable here. Now, slope. How do you calculate our slope? Slope is equal to change in what you have on the vertical axis. Change in f all over change in extension. Please, on no condition should you use change in x all over change in y when you plotted f against e. Please, there is a red flag. Now we have here, what do we have here? Remember, this is my 5. Here is 6. I can have here as 5.1 or 5.2 as the case may be. Minus what I have here, because here it's 2. I can have here as 2 all over. Now here, remember, this is my 25. This is 30. Of course, this is almost half. So, which will now give me, between 25 and 30, half of this line should give me 27.5. So I can have here 27.5 minus, remember here is 10, here is 15. It's not up to that. I can use here as 11 or 12 as the case may be. So I can have here as 11 or 12 as the case may be. Which will now give us 5.2 minus 2 will give me 3, right? Will give me 3.2. 3.2 all over 27.5 minus 12 will give us 15.5, which will give us now 3.2 divided by 15.5 will give us 0.21. 0.21. Now, do you leave it like that? No, you don't just leave it like that. It must have SI unit. Remember, this one is in Newton, this one is in cm. Therefore, you can now have that your slope is slope is equal to 0.21 Newton per cm. So this is the slope of the graph. Now the next question says, let's look at the next question. The next question says, all right, what does the slope of the graph represent? What does the slope of the graph represent? So look at, when you plot a graph of F against E, what do you have as your slope? Now, the slope, of course, if you have this against this, we'll say that the slope represents the force constant, or stiffness. You can say it represents the stiffness of the material. Either force constant or the stiffness of the material. IC says a rubber gun is used to project a stone of mass 40 grams. If the rubber gun, a rubber gun is used to project a stone of mass 40 grams. If the rubber of the gun has an elastic constant of 350 Newton per meter and was stretched 4 centimeters, calculate the stone's speed of projection. Now remember, we have a rubber gun. We said it was used to project a stone. Now the mass of the stone is 40 grams. Now if you have it to be 40 grams, they said if the rubber of the gun has an elastic constant, of course, K there, the force constant there is 350 Newton per meter, and it was stretched 4 cm. So if it was stretched, that means the extension there is 4 centimeters. Now they said calculate the stone's speed of projection. How do we solve this? Stone speeds, V. That is what we are looking for. Remember, this one is in Newton per meter. Because of that, take this one to meter. Take this one also to kg. So if we take this one to E, will give us 4/100, right? If you take it as 4/100, it will now give us 0.04, right? 0.04 meters. Why this one? Divide this one by 1,000. M will give us 0.004. 1, 2, 3. No? That means 0.04 kg. That is what you have. Now, how do you find the speed? What is the connection between this? And of course, you know where this thing will take us to. It will take us to the energy stored. What is the formula for energy stored in an electric spring? The energy stored here is equal to either half Fe, or you can say that energy stored is equal to what? Half Ke squared. Either you use this or you use this. And the same energy, also, energy is equal to half mv squared. Simple. So we are going to equate these two. Energy is equal to this, and the same energy is equal to this. We're not going to use this because we're not given force. We are going to use it because we are given a K. Therefore, we can now say that energy is equal to half Ke squared, and the same energy is equal to half mv squared. So we equate these two together. If we equate these two together, we're looking for V. We make V the subject from here, and if we make V the subject, we're going to have, if you rewrite this so that it can help you, if you write this, you know this thing is something as writing Ke squared over 2, right? And this thing is something as writing mv squared over 2. You can now handle this. If you cross multiply here, you will now have 2Ke squared is equal to 2mv squared. We're looking for V. Make V squared the subject. V squared will give us what? 2Ke squared all over 2m. And of course, this one will take care of this. We will now have that V is equal to the square root of KE squared all over M. Now, if we substitute into this, what do we get? We now have that V is equal to the square root of K. K is 350 multiplied by E. E, remember our E, we use the converted one, that is meters, so which will give us 0.04. Remember, there is a square here. Everything is all over M. The mass is 0.04. When you have this, V will give us square root of 350 multiplied by the time you expand these, which is 0.04 squared, it will give us multiplied by 0.0016. Okay, now everything is over 0.04. This time this will give us square root of 0.56 divided by 0.04, and V will give us the square root of, so 0.56 divided by 0.04, it will give us 14. Now the square root of 14 will give us 3.74 meters per second. That is the speed of projection of that stone. Now we have the number 9D question. 9D question of 2025 WAEC question. It says, question I, define bulk modulus. DII says, a vertical wire is suspended from a support with a mass of 2.5 grams attached to the free end of the to stretch the wire. If the load on the wire extends by 2 centimeters, determine the energy gained by the wire. How do we solve this? Very simple. The first one is bulk modulus. What is bulk modulus? Of course, bulk modulus is nothing but you have, of course, you know, we have bulk modulus, we have a shear modulus. Now this one bulk and we have young modulus. Of course, this is a bulk modulus. Bulk modulus is just is a ratio of small applied pressure increase, small applied pressure increase to the relative decrease in volume of the material. Small applied pressure increase to the relative volume decrease of the material. Therefore, we can now have that the bulk modulus is just a ratio of small change in pressure, all over we have a change in volume of that material, change in volume of the material. Or you can say small change in pressure, or you can say pressure increase, small pressure increase. Let's say small pressure increase, small pressure increase. You can take it this way, simpler this way. 2, decrease in volume. To decrease, you can say to decrease in volume of material. Of course, that is the definition of the bulk modulus. Of course, it is a ratio of small increase in pressure to a slight decrease in volume of that material. Now let us look at the second question. Now if we want to solve the second question, how do we solve the second question? So a vertical wire is suspended from a support with a mass. Of course, we have the mass. This is a solution. We can divide this into two. Now have the mass M there is 2.5 grams. Immediately move it to kg by dividing by 1,000. If we divide the 2.5 by 1,000, if we divide it by 1,000, it will give us 0.0012. 1, 2, 3. Yes. It should now give us 0.0025 kg. That is what you get there. Now, attach the free end to stretch the wire. If the load on the wire extends it, if this load now extends it by, that means the extension there is 2 cm. Move it to meters. To move it to meters, to give us 0.02 meters. 1, 2. All right. Now, determine the energy gained by the wire. We're looking for the energy gained. Energy gained by the wire. Of course, you know that energy gain is just the energy used in stretching that wire. And of course, energy there is E is equal to half KE squared. Now, if this is this, now what is K? K is not there. K, we don't have K. What is the formula for K? From Hooke's law, we know that from Hooke's law, we know that F is equal to KE. F is equal to KE. But then, what is our F? F is not here. Rather, they only gave us M. Recall. Now, we recall that F is mass times acceleration due to gravity. That is why we are given this. So, we can now use this to get our F. Therefore, F will give us mass. Mass is this, 0.0025 multiplied by 10. Therefore, the force there is 0. To multiply this thing by 10 to give us 0.025 Newton. I think that is what you are going to get. You can press your calculator to find out. Now, if this is our F, now we can now come here to say, make K the subject. K will give us F over E. F over E, which will give us F is 0.0025 all over the extension. Extension here is 0.02. Now, which will give us that K is equal to, now, if we do that division 0.0025 divided by 0.02, we will now have that K is 0.125 Newton per meter. That is what our K is. Having gotten our K, we can move ahead to substitute into this to get our energy stored. Therefore, energy stored is half KE squared, which will give us half times K, 0.125 multiplied by E. E is 0.02. Remember, it is squared. So if you deal with that one, you now have the energy is half multiplied by 0.125 multiplied by square of that value there, 0.02 squared. The value will give us 0.0004. And E will now give us, I'll multiply everything, that multiplied by 0.125 is equal to this divided by 2. Therefore, it will give us 2.5 times 10 raised to power 1, 2, 3, 4, 5 raised to power minus 5 joules. So this is the value we have for the energy stored in this. Therefore, this is where we are going to end this lesson today. Please like and share this video for more updates. Thank you very much.